This is our last video for the semester, Unit 8, Day 8. So what we're going to do today is coming back to something we actually talked about in Unit 1 first, which is permutations and combinations. So first thing we're going to do is just go over the definitions for these two and the difference between them. So first, a permutation. Permutation is an ordered arrangement of items in which um, no item is used more than once, so no repetition, and the order of the items makes a difference. And that's the key for permutation, is the order. That's permutation. So it's we're picking items, certain number of items out of a set, and putting them in order, and the order actually matters. That's different than a combination, which doesn't care about the order, just cares about what item you choose. So definition for combination: an arrangement of items in which no item is used more than once, so still no repetition. So no item is used more than once, and the order that the items are in makes no difference. So those are the full definitions. So just kind of the upshot is with permutation, order matters, and with combination, order doesn't matter. And that's the main way we distinguish between them. So we actually look at permutations and combinations. We're looking at how many different arrangements we have. So with combinations, the order of that arrangement doesn't matter. With permutations, it does. So we have two different formulas we use, and some notation that we've seen before. So for permutations, we have this notation. That's permutation of n things taken r at a time is the way we say that. And the formula is n factorial over n minus r factorial. So here n is the total number of items, and r is number of items you're choosing out of that total. And for combinations, similar formula, just one little difference. We have n factorial over r factorial n minus r factorial. So from the last video, you should recognize this formula is the same as the binomial coefficient. So that's why we use these notations interchangeably with combinations and binomial coefficients, because it's the same formula. But the n and the r here still represent the same thing as they do above. So we're going to go through two examples of actually using these formulas in a problem, distinguishing between permutations and combinations, and that's going to be it. This one in poker, a person's dealt 5 cards from a deck of 52. How many different 5-card hands are possible? So first thing we need to ask is, does order matter? So here all that matters is what cards we get, not the order that we get them in. Doesn't matter if we get an ace on the first or the last one, we still have an ace in the hand, and that's how we put our poker hand together. So here the order does not matter. That means that this is a problem involving combinations, not permutations. So here the total number we're choosing out of is 52 cards, and from those 52 we're choosing 5. So we're going to use our formula. Be 52 factorial over 5 factorial and 52 minus 5 factorial. So just like on day 2 of the unit, we're going to write this out, so we're going to have some cancellation. This will be 52, 51, 50, 49, 48, and then 47 factorial. And the bottom will have our 5 factorial and another 47 factorial. These will cancel out. And I can get some more cancellation if I rewrite this 5 as 5 times 4 times 3 times 2 times 1. We can cancel out 5 and 50 as 10 over 1. 4 and 48 is 12 over 1. 12 over 3 is 4 over 1. And then we can even go 2 over 4, or 4 over 2 is 2 over 1. So we end up with 52 times 51 times 10 times 49 times 2. Which comes out to 2,598,960. So this is how many possible different 5-card hands there are, coming from a standard deck of 52. If we're using permutations here where the order mattered, it would be a much bigger number, because it would matter not just the 5 cards you have, but also what order you actually are dealt those cards in. So this one is a combination. There's our answer again. We're mainly just using the formula like we have been in this unit, making sure we understand the formula and plug into the right part. So last question, we'll work through the same way as the last one. Coaching a Little League baseball team of 13 players, you need to choose a non-player batting order. So how many different lineups are possible? So again, I want to ask, does the order matter? Right, and this one is a batting lineup, so it does make a difference whether you're batting first or last in the lineup. It's a different order, um, depending on where you put those players. So it's not just the 9 players you have; it's the order that they're in. So order does matter here. Right, since order matters, that means this is going to be a problem with permutations. So we're choosing out of 13 players, and from those 13, we're choosing 9. So this is going to be permutation of 9 out of 13. And again, we're just using that same formula. We got 13 factorial over 13 minus 9 factorial. So this will be a little bit longer to write out. Will be 13 times 12 times 11, 10, 9, 8, 7, 6, 5, and finally 4 factorial. And 13 minus 9 is 4 factorial on the bottom. So these will cancel out. Here our final answer. Very big number, so making a non-player batting order out of 13 players, there's 259,459,200 possible lineups you can make. So take it easy on your coaches. That's a lot of lineups. That's it for this video, and that's actually it for all the videos. It's the last video for the semester. If you want to look up any extra resources or any other videos to explain this better, you can search for permutations and combinations. There are a lot of videos on this topic, so you shouldn't have a hard time finding those.